In this video, we're going to introduce a new peripheral, the AVR ADC. Let's start, as always, in the datasheet. At a high level, we can see that the ADC on the AVR is a 10-bit successive approximation ADC. Let's have a look at the block diagram. We can see three major aspects here at which we'll set up some control logic for the ADC. The ADC multiplexer select, AMUX register, will focus on selecting the input voltage reference for the ADC. So we can have an analog voltage reference, AVC, or an internal 1.1 volt reference, or an external reference. Then the multiplexer will select a particular ADC channel, and we can see that there are a number of channels available to us. There's a control and status register, which is involved with a prescaler of the clock to the ADC. And then finally there's a result register. You can see that it's a 16-bit because 0 to 15, but remember it is a 10-bit ADC. So let's scroll and look for some interesting things to point out. When we're looking at prescaling and conversion timing, what is important is that the successive approximation circuitry requires an input clock between 50 and 200 kilohertz to get the maximum resolution. The voltage reference indicates the conversion range of the ADC. If we're wanting to get the full range of the ADC, we should set analog VCC and set this equal to VCC. To understand what the conversion result means, the ADC result register is equal to the input voltage times 1024 if we're using the full 10-bit resolution over the voltage reference. So keep that in mind with our result. So we're on the registers already, so let's open a new project and start coding. Let's set up a function ADC init. The first thing we wanted to do was set up AVcc as our ADC voltage reference. Next, we need to choose an ADC input channel. Let's choose ADC 1. And let's figure out which pin that's connected to. So we can see ADC 1 is connected to port C1. So when we get to testing the ADC, we have a potentiometer, and we've got to make sure that the middle terminal of this potentiometer is connected to port C1. The next register to have a look at is the status register. And we're going to enable most of the bits in this register, and I'll explain why. ADC enable, well, we're going to enable the ADC. SC is to start a conversion. We're going to want to do that. ADATE is ADC Auto Trigger Enable. We want this enabled because we want to run in free running mode, continuous conversions, and we'll see a little further on when we set a trigger source of nothing, we are in free running mode if ADC Auto Trigger Enable is written to 1. So we need this written to enable our continuous conversions of the ADC. Next, there's an interrupt flag and then an interrupt enable. So we want to enable ADC interrupts. And finally, we need to select a prescaler. So recall that we needed a frequency for the ADC of between 50 kilohertz and 200 kilohertz. So our clock frequency is 8 megahertz because we are running this board at 2.7 volts. So trying a prescale of 64, we can see that that gives us a ADC frequency of 125 kilohertz, which is fine. So we need to set the prescaler bits 2 and 1. Okay, recall that we have enabled interrupts, and therefore we need to add the interrupt header file, AVR interrupt.h. Now we can create an interrupt service routine for the ADC. In our ADC interrupt vector, let's simply toggle a LED. So I'm going to paste in a few macros that we defined in some of the earlier videos to work with LEDs. Let's quickly set up this board. We remember that we needed to pin C1, and we need to connect the other two to 5 volts, well, to VCC, which is set to 3.3, and to ground. Now we can test. And let's step through this function so we can see how we set up the multiplexer, selecting a reference and a particular ADC channel. We can see the status register and all the individual bits that we've set up here. And let's set a breakpoint in our interrupt service routine. So we can see we hit the breakpoint, and we can now have a look at the results register, the ADC register. And as I move the pod, we can see the value changing. So moving it all the way to the left, we can see that we have the maximum value of the ADC. Turning it all the way the other way, it's off, and something in between, we get an in-between value. So let's have a look and see if these readings are as expected and predicted by the datasheet. Taking a voltage meter, I'm going to measure my VCC, and I can see it's at 3.297, which is pretty much as expected, and we'll round to 3.3. And the voltage on the ADC input channel is 1.104. Let's see what we should have been measuring from the datasheet. Our reading was 156, which in decimal is 342. And we're going to multiply the ADC by the voltage reference and divide by 1024. And we can see that this is a value of 1.102. We measured 1.104. So it's pretty close. If you'd like even more accuracy, I point you towards a specific application note, AVR 120, Characterization and Calibration of the AVR ADC. But thanks for watching this introduction to the AVR ADC, getting up and running nice and quickly, and continue watching to look into some more advanced use cases.